Good evening, at least it's evening for me. This is going to be my first ever calculus video. I'm not starting at the beginning of calculus like limits. I'm starting somewhere in the middle, and then I'll fill in with more videos later. So I'm starting today with the concept of maximums and minimums. In a function. So maximum minimums fall under the umbrella term of extreme values. So I'm going to start with that vocabulary. Extreme values. And extreme values are simply highest or lowest y values of a function. And so we divide those into two categories, maximums and minimums. And I'll put in parentheses here, we're talking about y values, not x values. So when you're looking for a max or you're looking for a min, you're looking for the highest y value or the lowest y value, not the highest and lowest x values. So here are a couple of examples of functions that we're very familiar with that may or may not have maximums and minimums. So this is one of my go-tos, y equals x squared. We all know that this is a parabola with a vertex at the origin. And we can see from the graph of the parabola that there is a lowest point at 0, 0. So there is a max at 0, 0. But there is no minimum, so no min. There is no min. So this function has a max at 0, 0. I mean, sorry. That's backwards. This function has a minimum at 0, 0. And no max. If I turn that upside down, y equals negative x squared, it turns the parabola upside down, and now the max is at 0, 0, and the min, well, there is no min. This third example is a cubic. And we should all know that that looks like this. And we can see from the graph that there is no max and no min. Okay, so there's a little intro as to what maxes and mins are, how to identify them from graphs. Most functions are not that simple looking. Here's one that is much more complicated. We're not going to plot it ourselves. I've already pre-graphed this so I know what it looks like. So this one starts up here, goes up like this, down here, and goes up here. Now, because I want to talk about endpoints, I'm going to cut this function off at both ends. So I'm going to start it at x equals -1 and end it at x equals 4 so that we can talk about this interval. Okay, and I've already plotted some of these points. This is -1, 37, that endpoint right there. This is the origin. This is 1, 5, and this is 3, negative 27. And the other endpoint is not really important to me right now. So this function, as you can see, does have a max. So the max is at negative 137, and you can see here there's a min at 3, negative 27. However, there's also this other point here at the top of this hill, 1, 5, which is important, maybe not as important as the two extremes, but it is called a max as well. You're wondering, how can we call it a max? It's not the highest point. Yes, it's not the highest point, but locally in this neighborhood, around this little hill, it is the max. It is the max. So we can call it a local max. The negative 137, since it is the highest point in this interval of this function, is called the absolute max. So that's how we distinguish between the two. Absolute max is the highest of the entire function. Local max is just the top of a hill in the neighborhood, in the local neighborhood. The 3, negative 27, that is definitely the lowest, so that is an absolute min. An absolute min. And, oh, I forgot about this. The origin. There's a local min at the origin. And could you say that 3, negative 27 is also a local min? Yes, you could definitely say this is a local min. The fact that it's the absolute min, though, is probably more important information for us, so we generally just call absolute mins absolute mins. And absolute maxes, we generally call them absolute max, because that's more important information to us than calling it a local max. Now, you might wonder, what about the endpoint over here? Is that a max? Is it a local max? It's definitely not an absolute max. It is not a local max, and I'll explain either later in this video or another video why it's not a local max. Okay, so now we want to talk about what critical numbers are, and that's what I'm going to end with. You've actually already seen some critical numbers when I was talking about maxes and mins. So a critical number is, first of all, it's an x value, not a y value. It's an x value where f prime of x equals 0, or f prime of x does not exist. In other words, it's an x value where the slope equals 0, or slope does not exist. Well, at what points on a function, a continuous function, is the slope 0? At maxes and mins, right? What we were just talking about. So critical numbers are simply the x values of those maxes and mins that we were talking about. But it's just the x values, just the x values. Those are the critical numbers. Now, what about the places where it doesn't exist? Where does that happen? Well, if we're only talking about continuous functions, then a slope would not exist if the curve did this. And sometimes we'll get functions that have a sharp turn like this, there is no slope at that point. No slope. Whatever point that is, there's no slope there. The curve must be smooth, in order for there to be a slope. We call that being differentiable. So it's differentiable everywhere here. It's differentiable everywhere here, but as soon as you get to this point, that point is not differentiable. There is no slope there. So the definition of critical numbers here, when it's talking about the x values where the slope is 0 or when the slope does not exist, they're talking about points like that. They're also talking about endpoints. So let's say here's your curve and then it all of a sudden stops there. F prime of x also does not exist right there. It's smooth, and then at the endpoint it's not smooth. I know you could argue that it is smooth, but it really isn't. So there is no slope there. So these are the two scenarios where you would have no slope. And these are still called critical values. Okay, all of these are critical values. Where there's a max, where there's a min, the x value is the critical value. Where there's no slope, when there's a sharp turn, no slope, or at an endpoint, no slope, the x values are the critical values there. So we can put all this together in an example of a graph. Let's say we have a graph that looks like this. And I will label these x values with just letters. And every single one of these are critical values. So A, B, C, D, E, F, G, and H are critical numbers. Critical values, critical numbers. Why is that? Because at every one of these values, A through H, the slope is either 0 or does not exist. So let's go through these. At A, f prime of A does not exist because that's an endpoint. At B, that would be this point up there. F prime of B equals 0. And it happens to be a max. Or f of B happens to be a max. At C, the slope is 0. That's a min. Whoops, min. At D, that's supposed to correspond to that one. C is here. Slope is 0. At E, slope is 0. At F, slope is 0. Now when we get to G, we finally get a does not exist here because of that sharp point there. And at H, it's an endpoint. So the slope does not exist there either. Let's go back here. That's a max. That's a min. That's a max. And the one at F, that's an absolute max. Absolute. And I didn't draw this very clearly, but I think the E is supposed to be the absolute min. And the other three here, these are local. These are local. Okay, so that's the concept of maxes and mins and the relationship between critical numbers and maxes and mins. Thanks for watching K109 Math, and we'll see you later.